Hello and welcome to this session on the art of Java type patterns. My name is Simon Ritter. I'm the Deputy CTO at Azul. The idea of this session is to talk about how patterns have been introduced into the Java language. And as we'll see, there are a number of different ways that this has been included, affecting a number of different aspects of the way that we use Java. The first thing to do is to understand a little bit about the fundamentals of what we mean by pattern matching in this particular case. And this is something that's a very well-known technique. It's actually been around since the 1960s. And if you've ever had the chance to use some of the older languages, things like Haskell or even Awk, then you'll be familiar with the way these things work. What we actually mean by a pattern is two things in this case. So we have, firstly, a match predicate. And the match predicate is what we're looking to find and match against. So it's a binary thing. We either match it or we don't. It's true or false. What that does is determine a target that we're going to match against. And we'll see lots of examples as we go through. If we match something in terms of that predicate and it returns true, then we will have 0 or more pattern variables that we're going to make referenceable based on the fact that we've matched that pattern. So we'll conditionally extract the values of those variables and make them available for the rest of the code that we're going to be using. So this is the fundamental idea of pattern: match predicate, pattern variables. Let's start then by looking at some fundamental parts of Java and how we can apply patterns to them. First of those is the instance of operator. Clearly, this has been in Java right from the very beginning. Java is an object-oriented language. We can have lots of different classes and we can have inheritance. We can also have interfaces. And one of the things about this is that by using polymorphism, we can view an object as any of the types that it actually implements, whether that's the concrete type it implements, any of the superclasses of that, or any of the interfaces that the concrete class or its superclasses implement as well. In order to determine if an object that we have a reference to is one of those specific types, we use instance of. We're all familiar with this. And here's a very simple example. So I say if obj instance of string. So we're looking to see whether the reference we've got is of type string. If it is, then we want to use it as a string. In the true branch of our if statement, the first thing that we have to do is to create a new variable called s of type string, and then we assign that the reference to obj, and we have to do an explicit cast to say that it's a string. If you look at this code, you could really kind of argue, well, is this actually necessary? Realistically, it's quite redundant having to do this, because you could say, well, if we've determined that obj is of type string, surely in the true branch, we could just reference it as a string and we don't have to worry about casting it and assigning it to a different variable. But this is the way that Java works. This is the way it was designed. And so we have to have an explicit new variable with the cast. Once you've done that, we can obviously reference s and we can call methods on it in the way that we would normally do for a string. How can we improve on this with pattern matching? Well, we have pattern matching for instance of. This changes our code slightly, and we can see here that we now have if obj instance of string. So this is our pattern predicate. We're looking to see whether we match obj as being of type string. If it is, we have a pattern variable called s, and that will be assigned automatically the value of obj, and we can treat it as a string. In effect, what we've done is remove that line of code where we did the assignment with the explicit cast and moved it into the instance of operator by referencing the variable name that we want to use there. Now, clearly, in terms of the scope of s, where we can use it in a valid way, it's in the true branch of that if statement. So if we do match against type string, then the true branch will be able to use s and we'll have the ability to call methods on that, as we can see. However, in the false branch, the else, because we haven't matched a string, we don't then have a valid variable s, so we can't use it in that case. Now, we can take this a little bit further, and we could include an AND operator. So now we can say if obj instance of string, so our match predicate, and have our pattern variable s, but then we can add onto that a test to see if s.length is also greater than 0. Now, this will work quite happily because we know that the way that the AND operator works in Java, it uses short circuiting. So we will always evaluate the left-hand side of the AND operator, and only if it equates to true will we evaluate the right-hand side. So long as it equates to true on the left-hand side, we do have a string. The scope of s is valid. So when we come to evaluate s.length, we have a valid reference and we can use that. If s is not a string, if object is not a string, then we won't have to test the right-hand side because we'd fail. Similarly, that means we can't use the OR operator for the same reason that we're having that short circuiting. In this case, we know that we would always call the left-hand side of the OR operator, and only if it equates to false would we call the right-hand side. If it equates to false, we don't have a reference to a string, so it doesn't make sense to be able to try and use s on the right-hand side, so we would fail and the compiler would not allow us to do that. Now, the thing that we need to understand here is that scoping of our pattern variable can be slightly counterintuitive. Here I've got an example where I've inverted the test. So in this case, I say if not O instance of string. So if it isn't a string, then we're going to return from the method. What that means is that for the rest of the method, we do have a pattern variable s that we can reference. So we can print out the length, we could have several hundred lines of code, and we could then print out the length again. S is still in scope. So be careful when you're inverting the test to make sure that you understand about how the scoping works. And the way that scoping works, we need to go into it a little bit more detail because it's not the same as local variables in Java. If you look at local variables, the way that they're defined in terms of their scope is that the scope is valid from where the variable is declared to the end of the block in which it is declared. Now, whether that's an explicit block of code using braces, whether it's an if statement, whether it's a for loop, a while loop, or whatever. But that's the scope of a local variable, or even within a method. The other thing about local variables is that they are subject to definite assignment. You cannot leave a local variable to have a default value. There is no default value, not like instance fields. So in the case of local variables, you have to make sure that you assign a value to that. Otherwise, the compiler will complain and not compile your code. In terms of our pattern binding variables, they are also subject to definite assignment. But in this case, the scope of our variable is all the places where it will have definite assignment. It will have an assigned value for it. If we look at the case of the if statement, the scope is where it definitely has assignment, which is in the true branch, but not in the false branch. So the false branch doesn't get included as the scope because it doesn't have a definitely assigned value. Now, what we call this is flow scoping. So it works in slightly different way to local variables. And we can look at an example of that because one of the things we can do, which we couldn't do with a local variable, is this. We can say if O instance of integer and then use a pattern variable called num. And then if that fails, we can have else if O instance of float. And then we can reuse num as our variable name, remembering that the scope of num will only be in the true branch of each of those parts. Similarly, we could have another one else if O instance of long and reuse num. Now, we couldn't do that with local variables, but because of flow scoping, we can reuse the same variable name in those three different situations. And that's actually a really nice feature because it does mean that we're able to avoid having to, have multiple different variable names like num1, num2, num3. Now, we can extend pattern matching to other areas of Java. One of those is switch. So this was another thing that came a little bit later than pattern matching for instance of. And if we look at the way that switch works in Java, up until now, you've been fairly limited in what you can switch on. Essentially, you can switch on an integral value, a number, strings, or enumerations. What we've now done is expand that to allow patterns to be used on types. Here's an example. So I've got a type tester, I pass in an object reference, and then I switch on that. What I'm then going to do is look for certain types and do something based on whether that's true or not. First one of those is case null. Now, that's a new thing for the switch statement, switch expression, is that we can have an explicit case for null. We couldn't do that before, but now we can. And that is very useful because the way we would use switch before is most of the time we would have to have a test outside of the switch statement in order to test for null and then maybe throw an exception if that was the case. Now we can include that into our switch, and that makes the code tidier and easier to understand. Obviously, in terms of a pattern, null is null is null. So there is no variable in there. It's a fixed value. So we don't need a pattern variable for that. However, if we look at the other cases that we have, we've got string as our pattern predicate. So we're looking for that type. And then we're looking to see that the variable we're going to use is s. And we can then use that on the right-hand side of the arrow operator to print the string out. Similarly, if we've got a color as our match predicate, we'll then have a variable c, that's the pattern variable, and we can then call the color methods on that, get RGB on the right-hand side. Now, primitives in Java are not types in the way that everything else is, but arrays of primitives are. So we can't have a case yet, not until Valhalla comes out, but we can't have a case for a primitive, but we can have a case for a primitive array. As you can see here, we've got case int array, and we called it IA, and then we can print out the length of the array on the right-hand side. Now, a little bit more about null, because null is a little bit special. So case null, obviously, we added that explicitly in the example that we had before. We don't have to do that. And to maintain backwards compatibility, the compiler will insert a case for us if we don't do it explicitly. What that will do is throw a null pointer exception, so you would get exactly the same behavior that you would have done previously, and it maintains that backwards compatibility. Again, let's just look at an example here. Using our type tester, we can switch on O, but we don't explicitly put in a case for null. We've got string, we've got color, we've got int array, and then a default. Default will not catch null. That's quite an important thing to note in this case. Again, it maintains backwards compatibility. So what actually will get compiled here is that the compiler will insert a case null, which will throw a new null pointer exception. And again, it will behave in exactly the same way. But what we can also do is we can say to ourselves, right, it might be a situation where we want to handle both anything that's not explicitly listed in our set of types and null in the same way. And we can do that because we can take advantage of some of the new syntax that's been introduced more recently in the way that switch statements and switch expressions work. So we can say, right, case string, case color, case int array, but then we can also do case null, comma, default. And that means that any type other than the three that we've got there and null will be handled in exactly the same way. So it's a nice little tidying up feature that allows us to handle those types of things. Now, the other thing about pattern matching for switch is that we need to have completeness. And what we mean by this is that all of the possible types must be handled by our switch. Let's look at this example here. Got my type tester again, switching on O. But this time I've only specified two types, string and integer. Now, what happens if I pass in a color or a float or an int array? Well, you could argue that because there isn't a case for those and there's no default, then there is nothing to do, and we simply drop past the switch and carry on with whatever code goes below that. But that's not the decision that was made. The decision by the developers of this feature was that that would lead to too many potential bugs that could be hard to find. So what we must do is we must ensure that we have every possible type covered. In this case, we couldn't do that by listing every single type that we could have because it would be an infinite list. To get around that, the obvious way is to include a default statement. If it's not a string, if it's not an integer, we will handle everything else by the default clause and we'll print out it's some other type. However, what this does mean is that we don't have to have a default for every single switch statement or switch expression that we're dealing with. How can we do that? Well, another feature that was included in Java more recently is what are called sealed classes. Here's an example of one. So we can have public sealed class shape, which permits 3 subclasses: triangle, square, and pentagon. That gives us a type hierarchy, which is sealed. So there are only 4 possible classes involved there: shape, triangle, square, and pentagon. If we wanted to, we could modify our code and we could have a type tester which took a shape as a reference, and then we could have a switch on shape. And now we can list triangle, square, pentagon, and shape, and we don't need to have a default statement. The reason for that is because clearly we have covered all the possibilities in terms of our type hierarchy, because we've got all 4 possibilities represented there. There is nothing else that could fit in there. Now, another thing that we can do is we can have what are called guarded patterns. This sort of comes back to what we were talking about with the pattern matching for instance of, where we could see that we would have the ability to say if obj instance of string s and s.length is greater than 0. That's in effect a guard that we put on there. We can do that in our switch expression and switch statements using a slightly different way of doing it. Initially, they did use the AND operator, but then in JDK 19 or JDK 20, I can't remember which one it was exactly, they switched to using when. So what we can now do is we can say, right, switch on shape, and we'll have a case triangle t. So that's our pattern predicate with our pattern variable t. And then we'll have when to indicate that we also want to apply a guard to that, which is then a condition that needs to be matched as well. In this case, we'll do evaluate the t.area and test to see if it's greater than 25. If it is, then we can print out it's a big triangle. Again, to ensure that we have completeness, we must also have a case for triangle t on its own. Because if the area of the triangle wasn't greater than 25, we wouldn't have completeness. So we must have a case for triangle t, and then we print out it's a small triangle, and then we've got the same square, pentagon, and shape for the rest of them. So the syntax is this: is we have a primary pattern followed by when, and then a conditional and expression that will evaluate true or false. This only works in patterns, so you can't use it where you're matching against a value. So you couldn't do case string foo when and then do something else. It only works with pattern matching, so it must be a type with a pattern variable. The other thing to be aware of here is what's called pattern dominance. We could change the order of the cases that we have in our test, and this would result in code that wouldn't compile. Why is that? Well, what I can do here is I could say, let's move the shape to the top of that list. So now we have case shape, case triangle, case square, case pentagon. If we do that, because the type hierarchy is that shape is the superclass of triangle, square, and pentagon, clearly all triangles, squares, and pentagons are shapes. So when we did a test on case shape, everything would match, regardless of whether it was a triangle, square, or pentagon. What that would result in is a compiler error, because it means that the other 3 cases there become unreachable. There's no possible way that you could pass something in that wouldn't match on the first case for shape. And so those 3 lines become redundant. And to eliminate the possibility of you doing that by mistake and then ending up with very weird code and weird errors, it's much easier to have the compiler identify that and say, no, you can't do it. You have pattern dominance there. So those 3 lines are unreachable. You also need to be careful when you're using a guard, because again, that could provide dominance and hide code, make it unreachable lower down in terms of the cases that we've defined. Here I've got case triangle t on its own, and then I've got case triangle t when, with the guard, t.area is greater than 25. Clearly all triangles would match against the first case, so we would never get to the second one. We would never try and evaluate the size of the area of the triangle. And so we would have a situation where we were dominating the second one, the second case with the first one, and the compiler will reject that. So the way that this is defined is the specification says it is a compile time error for a label in a switch block to be dominated by an earlier label in the switch block. Makes sense. It just eliminates that problem and the possibility of errors. We can also apply pattern matching for instance of and records. Again, records is something that was introduced fairly recently into Java. And so we can do something like this. We could say, let's create a very simple tuple, a point, double X, double Y. We could then have the use of pattern matching for instance of with our record. Quite logically, we could say if O is an instance of point, so that's the type we're matching against, and then have the pattern variable P. That will give us a record reference. And then to access the values of that record, we can simply call p.x and p.y, assign those to local variables, and then we can calculate the hypotenuse's x squared plus y squared square root. However, we can do better than that. What we can use is a slightly different form of pattern matching, which is called record patterns. And this is what's called a deconstruction pattern. Rather than just matching against the pattern and assigning the variable, we're going to extract values out of the reference that we have and make those available separately. Now what we can do is we can say, okay, we've got our Pythagoras method, pass in an object reference and say if O instance of, and here we provide the record definition. So we say point, and then we have double A and double B. One thing to be aware of here is, and I've done this deliberately, is there is no requirement to use the same variable names for the record declaration. Obviously, you have to use the same name of the record in order for it to be identified, so it's got to be a point. But the two doubles don't have to be called X and Y. In this case, I've called them A and B. Compiler will be quite happy with that. There's no problems at all. We can then use those directly without having to do the call to the method to return the value from the record. We can simply reference A and B through that deconstruction pattern because we've declared them as part of that record declaration when we're doing the test on instance of. Now, the interesting thing as well is that patterns are composable. We can do something like this. Let's declare an interface called rectangle. We'll take our record called point with a double X and double Y, and we'll introduce an enumeration for color, red, green, and blue. What we can then do is have a couple more records to make things slightly more complicated, and we'll have a color point, which consists of a point and a color. And then we'll create a color rectangle that consists of a color as being a color point being the top left and a color point being the bottom right. And we'll also say that it implements rectangle just for ease of the demonstration here. So these are going to be records as well. What we could then do is use our deconstruction pattern with instance of, and we can say print color of a rectangle. So if R is instance of, and we'll test against the color rectangle record, and we'll use the deconstruction by giving it the definition of that color rectangle as color point top left, color point bottom right. And then we can use top left, and we can call the color on that using the reference to the record value. Obviously, we know that color point is also a record, so we could expand that further, and we can say if our instance of color rectangle, and then we can use the record declaration for color point, point P, color C, and then we'll call color point the bottom right, just simplify it to BR. Now we can just print out C. Great. But of course, we know that P is also a record. So let's just go one step further and say that we can have print top left X of a rectangle. So we say if our instance of, now we've got our record declaration for color rectangle, we've got a record declaration for color point, then we've got the embedded color declaration, record declaration for point, giving us double X and double Y, and we can print out the X value without having to do any deconstruction ourselves. Now, obviously, you look at that and you start to think, well, that's really nice, but it doesn't actually sort of simplify my code a great deal. It's getting very unwieldy with all these types and all these variables that I have to have when I'm only interested in one particular thing. And one of the good things here is that another feature that's just recently been added in Java, it came in JDK 21, and I think it went final in JDK 22, is unnamed variables and patterns. There are a number of different situations where we have to declare a variable with a type in situations where we don't actually want to use that variable. And what we're showing here with that previous example is a very good one, because we're only interested in the X value. We're not interested in the Y or the color or the bottom right. But we still have to declare them so that the compiler can actually identify the correct records and the correct structure of those records to make everything work in the right way. What we can now do is use an unnamed pattern where we replace those patterns with the underscore character. Single underscore prior to JDK 9 was a valid variable name. In JDK 9, they said, no, we're going to make it a reserved word and you couldn't use it as a variable name anymore. What we can now do is simplify our code by replacing those patterns that we don't want to use with an underscore. So here I've got my top left X, print top left X. If our instance of color rectangle, color point, we have to have the name of the record, point, the name of the record that we're interested in. Now we'll say X, but we'll also use var to simplify that. And then for the other things that we wanted, the Y, the color, and the bottom right, we don't have to specify any of the types, any of the variables associated with that. We replace all of those with a single underscore. Compiler's happy because it knows that there is something there, but it can fill in the details for us based on all the things that we've declared. So the important thing there is that both the type and the variable are replaced with a single underscore. The unnamed variables and patterns actually extends further than this, and it can be used in different situations with other variables and so on. We can also, as I said, use that in different places. Here's another example where we're using it in a switch. So we could say, okay, we want a type pattern for our switch and the different cases, but because we're not using the value, the pattern variable on the right-hand side, we're going to replace it with an underscore. So now we simply say string underscore and print out a message, color underscore, float underscore. Probably a little bit less useful than the previous example because it only replaces a single character, but again, it aids readability of our code and makes it clearer what's going on. Just to summarize then, basically pattern matching is a very powerful set of language constructs. It simplifies a number of different tasks that we do on a regular basis. It reduces a lot of the boilerplate code that we see in those situations, and it makes our code more declarative. So it's a big bonus in terms of aiding readability and reliability of our code. Something that's less obvious is that there's also the possibility that we could improve the optimization of our code underneath. The way that the JIT compiler can work, the way that the code generated, there are opportunities there to be explored in terms of improving the efficiency of the way these things work. A lot of things in pattern matching have already been added. I would expect to see some more things coming in the future. So, for example, arrays might have pattern matching included in them, and some other areas as well. So things to look forward to in newer releases of Java. So with that, I'm going to say thank you very much for listening.